15H is about graphing with polar coordinates. So there are such things as not only polar coordinates but polar graphs. So the graph of a function f in polar coordinates is simply the set of all points r theta such that r equals a function of theta. So this means the distance of points from the origin is a function of the angle from the x-axis. For instance, we might say, okay, well then if r equals theta, what does that graph look like? If our theta equals 0, then our distance from the origin would equal 0. If theta would equal pi on 4, r would also equal pi on 4, and so forth. Pi on 2 for the angle would be pi on 2 for the distance. 3 pi on 4 for the angle, 3 pi on 4 for the distance. And let's do one more. If we had pi for our theta, we would have pi for our r. We're going to sketch this graph, but before we do so, I'm just going to write the approximate value for pi on 4. That's approximately 0.79. Pi on 2, or 3.14 divided by 2, is approximately 1.5. 3 pi on 4, that's approximately 2.3. And pi, well, we know what that is, 3.14. That will help me sketch the distance from the origin of my graph. So let's plot some points in. When theta is 0, or I'm along the positive x-axis, my distance of my graph from the origin is 0. That means my initial point in green, or the point is 0, 0. That's where my graph starts. If I'm at an angle of pi on 4, the distance the point is from the origin is 0.79. So it's approximately 0.79 units along that yellow line of angle pi on 4. That's my second point. I'm going to keep plotting points and see what we have. At the angle of pi on 2, remember I would be at the vertical y-axis and the positive part of that axis, and I'm going to be 1.57 units up that axis. Somewhere here. Next, I have 3 pi on 4 as my angle. So that will be in the second quadrant. Somewhere here, and now my distance is a bit longer. It's 2.36 units from the origin. So that's my next point. So that's my next point. Lastly, I'm going to put one more point in. When we have the angle as pi, or that's taking me to the negative x-axis, and I'm going to be 3.14 units in that negative x-axis direction. So somewhere all the way between -3 and -4, I'm going to put my point on that x-axis. Now my graph is simply if I connect all of these points in a nice curved motion. Notice we get a spiral effect. As my angle gets bigger, so does the distance from the origin of that graph or those sets of points. This spiral could continue around and around, and it would keep going in this pattern. That is an example of a graph where r is a function of theta. Let's look at some more examples involving these graphs. So, when we're trying to convert polar equations to Cartesian equations or vice versa, it's important we use some facts. Here are the facts we're going to use. And remember, they just stem from the fact that if I have a point, xy, it can be written as r theta, where x and y I have, theta is the angle, r is like my hypotenuse. Then we can say sine theta equals y on r, or that r sine theta equals y. I also have that cos theta would be adjacent over hypotenuse, x on r. And that can be rearranged as well to r cos theta equals x. And then, of course, by Pythagoras, I have x squared plus y squared equals my hypotenuse r squared. Let's use these facts to convert from polar form to Cartesian form. First example, a curve has a polar equation, r2 sine theta. Show that this is a graph of a circle with radius 1 when written in Cartesian form. So to convert from polar to Cartesian, we've got to get rid of the r's and the thetas. So eliminate those and be left with an equation that's just got x's, y's, and constants and coefficients. We use the three formulas that we have above. So notice from equation 2 up the top, I know that y equals r sine theta. I want to eliminate this sine theta part of my equation, r equals 2 sine theta. So where I see a sine theta, I'm going to sub in y over r. I will get r equals 2, sine theta becomes y over r. Notice I've got rid of that theta, that's good. Now I've got to get rid of the r. So I'm going to first take r to the left-hand side, and we will get r squared equals 2y. This is good because from equation 3 up the top, I know that r squared equals x squared plus y squared. So this time, wherever I see an r squared in the equation, I'm going to put x squared plus y squared. This will give me x squared plus y squared equals 2y. And I have eliminated r. Lastly, I've got to show that this Cartesian equation is actually a circle with radius 1. And remember the equation of a circle? That's what I'm trying to get this equation to look like. So I'm going to have to complete the square for the values of y here. The x squared can stay, that's fine. Let's look at the y. I could rewrite y squared minus 2y as a y squared minus 2y plus 1. But remember, if I add the 1, I've got to subtract a 1. That all still remains equal to 0. Then this y squared minus 2y plus 1 is a perfect square. It becomes y minus 1 squared. Of course, I have that minus 1 hanging over the end, so let's move it to the other side, and I'll get x squared plus y minus 1 squared equals 1. This is the form of a circle. X minus 0 all squared plus y minus 1 all squared equals 1. The center of this circle is 0, 1. And the radius is the square root of the number on my right-hand side, or the square root of 1, which is 1. That's what we had to show. Okay, let's try another of the same type. So I have a polar equation, 2 over 3 cos theta minus 4 sine theta equals r, and we have to convert into Cartesian form. So recall from my first equation, I could say that cos theta equals x over r just by rearranging. I can also say that sine theta equals y over r from equation 2. And I'm going to use this because I have a cos theta and a sine theta on my denominator of my polar equation. By subbing these in, to 2 over 3 cos theta minus 4 sine theta equals r, I'm going to be able to first get rid of my thetas. So we'll have 2 over 3 cos theta is just x on r, minus 4 sine theta is y on r. And on the right-hand side, I still have r. Now let's expand, and hopefully something will happen with the r's. So this really becomes 2 over 3x minus 4y. And remember, the r on the very base of the denominator will flip up to the top. And then if we take the r to the right-hand side, we'll notice that they should cancel out. R divided by r is just 1. And this is nice because I have 2 over 3x minus 4y equals 1. Again, you can leave it like this, or you could rearrange. Just be aware that you might have some restrictions because of the denominator. So I know that 3x minus 4y can't equal 0. And then if I rearrange, I can create this to look something like a line by multiplying the 3x minus 4y up. Then rearrange to get y by itself. I'll get y equals minus a half plus 3 on 4x. Okay, this one is the opposite. We're going to take this Cartesian equation and turn it into a polar equation. This one I quite like. We have to eliminate x and y and replace these with thetas and r's. All right, very easily we can see that we have x plus y equals 1, and I have something with r cos theta equals x. I also have r sine theta equals y from those first two equations up the top. This is great. I'm going to sub them straight into my equation. All right, this is what we'll get. X is r cos theta plus y, well, that will be r sine theta, and all of it equals 1. This is already in polar form, but remember we want r equals a function of theta. So we want r as the subject and all the thetas on the other side. So let's take r out the front. Just by factorizing, we'll get r bracket cos theta plus sine theta equals 1. And then I will just divide by cos theta plus sine theta. And this is my polar form. R equals 1 over cos theta plus sine theta. Something a little different. Now we know how to convert. We want to sketch the graph, the polar function, r equals 1 minus sine theta on a plane. So sometimes it's helpful to convert into a Cartesian form and then sketch. But another method we're going to try and use is to look at the graph of r equals our function 1 minus sine theta. So imagine you're sketching a normal trig function, but this time we'll have theta on the x-axis and r as my vertical axis. I'm just going to sketch this between, say, 0 and 2 pi, so we get a rough idea of what's going on. I'm going to put in points along my theta axis, so 0 pi on 2 pi, 3 pi on 2, and 2 pi in radians. And then I'm just going to transform sine theta to figure out what 1 minus sine theta would look like. The minus in front of the sine theta flips a normal sine function upside down, and the 1 as the constant shifts vertically my function up 1 unit. Nothing has changed with the period or the horizontal shift, so these two things are the same and the period remains at 2 pi. If I graphed a normal sine function, so sine theta equals r, my function will look something like this. Okay, now let's graph minus sine theta. That will just look like the flipped version across the horizontal axis. And now all I have to do from this minus sine theta is add 1 or lift my whole minus sine theta graph up 1. So this will have a new range between 0 and 2, and it will start at the point r equals 1. Mine's a bit rough, but I think we get the idea. Now to convert this to a graph on our Cartesian plane. It could also be a graph on the polar plane, that's fine. But we're going to use this graph in red to help us draw r equals 1 minus sine theta. I'm going to put some points in. When theta is 0, my r on this red graph is 1. When theta is pi on 4, my height, my vertical height, r, if you put this on the calculator, it's 0.29. For pi on 2, my vertical height for r, well, that's just pi on 2, right? It's at that horizontal axis. When theta is 3 pi on 4, I'm going to get the height of my graph as 0.29 again. When theta is pi, my height of 1 minus sine theta is 1. And I'm just going to put just 2 more angles here. I'm going to do 3 pi on 2 because I can see that r is 2 there. And I'm also going to do theta is 2 pi because I know the height of the graph there is also 1. Now what we do is we take this and we put it onto our plane. So when the angle is 0, the distance from the origin is 1. That means I'm going to go 1 unit along in my positive x direction. Next point, when the angle now becomes pi on 4, the direct distance of my point from the origin is 0.29. So it's not very far from the origin. I'm going to put my point in right here, making sure that it's pi on 4 is the angle from the positive x-axis. When our angle is now pi on 2, my distance from the origin is 0. So I'm going to be exactly at the point 0, 0 here. For 3 pi on 4, that's going to be in quadrant 2. Again, my distance is 0.29, so kind of symmetrical to what we have in quadrant 1. When theta is pi, so now I'm in the negative x direction, my r is 1, so I'm going to end up at the point negative 1. So I'm going 1 unit along in the negative x direction. When my angle is 3 pi on 2, I'll be in the negative y direction, and my distance in that direction is 2. So I go 2 units down along the y-axis, and I'll be at negative 2. And then notice when I get back to 2 pi, again, I'm going to be along the positive x-axis, and I'm going to end up where I started with r being 1. Now, all we have to do is join these points together in the order that they occurred. And this is pretty awesome. We end up with something that kind of looks like a heart, because I know you love trig so much and you love functions so much. So this is related to 15H and 15I, and be sure to have some fun and add some fun to your day.